Good afternoon, everyone. I'm Mahboubeh Shahrbaf, and this is a big pleasure for me to participate in this conference and present my results about the constraint on the mass of Sexaquark as a candidate for dark matter. Okay. What is Sexaquark? Sexaquark is a bosonic state with the quark content of UUDDSS in color, flavor, spin, singlet state. But since the quark content of Sexaquark is really similar to 2 lambda state, we start with the mass of 2 lambda. But there is a big difference between our assumption about the Sexaquark and 2 lambda state. 2 lambda are interacting via bosonic meson exchange forces, but Sexaquark is suggested to be 3 diquark, which are interacting via color exchange forces. So color exchange are really stronger than meson exchange forces. That's why we expect the Sexaquark to be really stable. And also regarding the size, it should be really smaller than 2 lambda state. But about the mass of Sexaquark, if 1 lambda decay, the mass of the products will be something about 2054 MeV. And if the 2 lambda decays, the mass would be 1877 MeV. Since we have learned from one of our member group, Glenisfer, that the 2 lambda decay is really unlikely for this state, we consider some mass between 1877 MeV to 2054 MeV in our first calculation for the Sexaquark. And we consider that Sexaquark could be almost stable in this mass range, or it can decay with a lifetime more than the age of the universe. And if the mass of Sexaquark is less than 1877 MeV, it's absolutely a stable state. So we started with this mass range. And in our first calculation, we tried to find the lower boundary for the mass of Sexaquark and then the upper boundary for the mass of this particle. I was lucky enough to be the last speaker today, so already you have learned a lot about the neutron star, their importance, the equation of a state, and why we consider dark matter in neutron star. So we know that the core of neutron star have this high potential for different degrees of freedom, like hypernuclear matter, deconfined quark matter, or even dark matter candidates to appear in this high density. For studying Sexaquark in the core of neutron star, we need the hadronic matter equation of a state. In my calculation, I used a generalized relativistic mean field theory, which is called DD2 model, for considering Sexaquark. Of course, I use DD2Y, which include hyperons as well. In this, in this approach, all particles, all degrees of freedom, which are all octet baryons and Sexaquark as well, also sigma, omega, rho, and phi meson, as quasi-particle, which has effective mass and effective chemical potential. This effective mass and chemical potential are defined related to the scalar potential and vector potential, and this potential are all meson exchange potential, and the strength of this coupling to mesons are density dependent. They are dependent to the total baryonic density in our model, and those strengths are somehow adjusted in a way to be in agreement with the atomic nuclear properties, in particular around the saturation density. So our model is working very well around saturation density. At higher density, somehow we have extrapolated our model. But regarding the Sexaquark, since we still don't know anything about the substructure of this particle, and still there is no experimental evidence of Sexaquark in, for example, heavy ion collision, in a very simplified assumption, we consider the mass of Sexaquark to be increased linearly by increasing the density. So this mass shift of Sexaquark is somehow considered as all medium effect on this particle. And it's somehow a way to somehow prohibit the instability of neutron star, because with a constant mass of Sexaquark, we will have this problem that in a very condensed matter, exactly after formation of this bosonic state, the bosocondensation occurs, and without a pressure gradient, the TOV equation doesn't have any solution, so the star collapse. So we need a positive slope of the mass shift, which is this x value, and the mass of Sexaquark is considered to increase with the density. For the value of this slope of the mass shift, we have calculated the slope of the mass shift for other octet baryons, and we have suggested some value for this x to be in agreement with the with the other octet baryons. So by solving the gap equation in this relativistic mean field, the grand canonical potential, and so the pressure and energy density as the equation of a state are obtained. You already heard that by appearing dark matter in the core of neutron star, the equation of a state is getting softer. Here the black lines are the here. The solid black line is pure nuclear equation of a state. This black dashed line is hypernuclear matter, and the colored line are hadronic matter with Sexaquark. But the mass of Sexaquark are considered to have two different values, a lighter value 1885 and a higher value 1941. I will tell you later why we started from 1885. And you see, the equation of a state with Sexaquark are softer, but by increasing the mass and the slope of the mass shift of Sexaquark, the equation of a state again is getting stiffer, but still not stiffer than the pure, for example, hyperonic matter equation of a state. And the onset of Sexaquark is increasing by increasing the mass and the slope of the mass shift. Here, the mass radius curve for all equation of a state which you saw in the previous slide are shown. You could see all this color region are the observational constraint for the mass and radius of the pulsars. The most important ones which should be fulfilled in all mass radius curves are the recent results from NICER around 2 solar mass regarding the mass and radius, and also at 1.4 solar mass. All this mass radius curve should pass these two regions, but you can see the only line which are fulfilled with the 2 solar mass boundaries are this red line, and the only one which can pass this region around 1.4 solar mass is this blue one. And none of them can fulfill both constraints together. This is what we call this as Sexaquark dilemma. And we try to find some solution for this Sexaquark dilemma in our model. Before going to the solution, I would like to show this curve, which is somehow the constraint on the mass and the slope of the mass shift for Sexaquark. We need the Sexaquark to appear before the maximum mass of hyperonic star. So the region above this red line should be excluded. Also, we need the Sexaquark to appear not below the saturation density and just above the saturation density. So the region on the left-hand side of this yellow line and the region below this magenta line are excluded also. This is the line which somehow guarantee the stability of neutron stars, since X should not have negative values. And this vertical line is 2054, which I discussed already. So the only region which is left is this white region. And the minimum value for the mass of Sexaquark would be 1885 in our model, and the minimum value for the slope of the mass shift would be 0.03. So that's why in our first calculation we focused on these values and tried to find a solution for Sexaquark dilemma with those values. In this paper, you could see all details about this Sexaquark dilemma and the solution, which has been introduced to be quark deconfinement. In similarity with Hypron puzzle, probably some of you heard about it already, we tried to make a phase transition from hadronic matter to deconfined quark matter, both with Maxwell construction and crossover construction. So we found a solution for the minimum boundary of the Sexaquark. In this new calculation, I again tried to find the upper boundary. So I used the non-local NJL quark matter equation of a state, which in another work by our group, the free parameter of this value, this microscopic method has been selected by Bayesian analysis because both diquark coupling and vector coupling are not really well defined. So we did some Bayesian analysis to find the favorable parameter of this quark matter equation of a state. And then this non-local NJL method was mapped to a very simple parameterization of constant speed of sound, which has 3 free parameters and can be obtained very easily. So we use this quark matter equation of a state, and instead of Maxwell construction, we tried to use an replacement interpolation construction, at which we have to somehow cross both quark matter and hadronic matter equation of a state. At this crossing point, we can introduce some value like delta P, which could be positive and negative. By solving the boundary condition at both this pH and PQ point, at which pressure and the density, which is the derivative of pressure with respect to chemical potential, for 2 equations of a state should be equal. Here, between hadronic matter equation of a state and this interpolated equation of a state, and here between quark matter equation of a state and again interpolated equation of a state. In this way, we will have still quark hadronic matter equation of a state valid at lower density, quark matter equation of a state valid at higher density, and in between, we say that none of quark matter and hadronic matter equation of a state are valid. But this interpolated equation of a state is valid in between, and we can have a mixture of hadronic matter and we can find quark matter in this region. So here you could see somehow why I didn't use Maxwell construction. For Maxwell construction, we need this correct crossing between hadronic lines and quark lines. But since in our model it occurs at very low density, around saturation density, and we don't expect Sexaquark to appear at that low density, so we tried a higher crossing point, which is somehow a wrong crossing, is called like reconfinement region. But at this reconfinement region, we introduce some negative value for the delta P. By a negative value of delta P, still at high density, we have quark matter equation of a state, and at low density, we have hadronic matter equation of a state valid. And in between, we have this crossover phase transition. Here, the results are obvious. You could see this dash color line are pure hadronic matter lines, that none of them can fulfill both constraint around 1.4 solar mass and 2 solar mass. But the solid colorful lines are the replacement interpolation construction, which we have employed here. You can see, obviously, that all of those lines can fulfill both constraint around 2 solar mass and 1.4 solar mass. And another result is that here, I showed the result for 3 different mass of Sexaquark, which is 2000, 1950 and 1900, and the value of the slope of the mass shift is the same for all of them, but this red line, which corresponds to 2000 MeV or 2 GeV, is passing this green region really marginally. So here we could see the maximum or the upper boundary for the mass of Sexaquark is this 2 GeV, which today I learned that this range for the mass of Sexaquark is somehow in agreement with other calculation which has been done so far. So it's a good result, and I would say that still the hadronic matter equation of a state need to be improved more, because itself cannot fulfill the tidal deformability around 1.4 solar mass, and probably by having a modified hadronic matter equation of a state and some probably experimental data from heavy ion collision regarding Sexaquark, this puzzle could be completed. Thank you.
Questions?
This is a very naive question, but I was just wondering: so you get these sort of mass radius relations, but are they really distinctive for this candidate, or could they be sort of confused for other things? So how degenerate are these curves if you detect them with other sort of types of dark matter? Do you know?
Sorry, I thought I got the question. You are asking how we get these lines for the mass radius curve?
I know. So I was asking, could you get the same line for another candidate for something that's completely different? So could we be sure if we measured this that we were detecting Sexaquarks, or could it be something else?
Could be something else, but for sure we cannot say that the result would be exactly the same. These results are first of all model dependent.
Yeah.
Work just in our model, but as I told, it's a good model which can fulfill all atomic nuclear properties around saturation density. And the mass of this particle is really important here.
Right.
So I'm not sure. I cannot say anything by sure for the other candidates.
Okay, thank you.
You're welcome.
Hi, so can I maybe ask a little bit naive question? But I don't really understand how can a strongly interacting particle be a dark matter candidate. So can you explain this maybe?
Actually, it is not a strongly interacting particle.
But it is a Sexaquark.
Yes.
And quark is strongly interacting.
The self-interaction is a strong interaction, but the interaction with the medium is not a strong interaction. How can I explain this for you? Let me think a bit more and we'll come to you, okay?
Okay, thank you.
I just would like to comment on this question. So despite quarks themselves are strongly interacting, this composite state is scalar charge neutral. In addition, it's like wave function, organized so that it's completely antisymmetric with respect to all the permutations. And that typically leads to relatively compact structures and weak interaction with whatever. We, for example, can see that in the case of lambda hyperon. So when checking its interaction with hadron medium using primitive models like hadron resonance gas model, not primitive, simple, we see that a parameter which controls that interaction strength, hardcore radius, is really, really small for that particle. So that could give, and why I'm referring to lambda, because it has quark content half of the Sexaquark one. So it could like give a hint of why it can be really, really weakly interacting despite being composed of something which interacts strongly.
So, question about what happens to the neutron star when the Sexaquarks accrete onto it, right? So if Sexaquark is the dark matter, there's some accretion rate. Is the mean free path of a Sexaquark as it enters the neutron star very short, or can it penetrate the neutron star very deeply?
In the neutron star?
Yeah, maybe we can discuss this later. It's just a question of, is it going to be stopped very close to the surface because it has strong interactions with the baryons, and as a consequence, most of the kinetic heat is deposited at the surface.
Doesn't have a strong interaction with baryons.
I mean, it has some short-range interactions with other baryons, right? That's how you got the mass.
Yes.
The mass shift was coming from interaction.
Yes, yes.
So I'm wondering.
But it is not strong that much to go adopt if it's stopped around the crust, or yeah, I'm not sure about this question.
Yeah, let's talk about it later.
Okay.
So if the mass to radius profile does not cross with the 2 solar mass band, means that the model is already ruled out, correct?
Okay, yeah. So the solution is passing the observational constraint of 2 solar mass. That's why we introduced this phase transition to quark matter as a solution. So the hadronic matter is not valid around 2 solar mass. Here we have quark matter. Hadronic matter for each curve is valid to some, let's say, deconfinement onset. For example, here is just this point. Before that, we have hadronic matter, but after that, we have quark matter. And the quark matter can fulfill both constraints around 1.4 and 2 solar mass. Again, for the next one, for the blue one, the deconfinement onset by increasing the mass of Sexaquark is shifting to higher density, but still at really high density, let's say both 1.4 solar mass and 2 solar mass, the quark matter equation of a state is valid.
Okay, I see. Thank you.
Are there any lattice simulations for this
Sexaquark?
Yeah.
Not yet.
Okay.
Not yet.
So I think we can close here this session, and thank again our speaker.